Hello everyone. Now I am going to explain about friction in pipes. Okay. When a gas or liquid flow through a pipe, the flow of fluid through a pipe is resisted by viscous shear stresses within the fluid and the turbulence that occurs along the internal pipe wall. So due to this, there will be a loss of pressure in the fluid because the energy is required to overcome the viscous or frictional forces exerted by the walls of the pipe on the moving fluid. In addition to the energy lost due to the frictional forces, there will be loss in energy when the fluid flows through fitting, such as valves, elbows, and contraction and expansions, these things. And its pressure is mainly due to the local flow separation as it moves through such fittings. The pressure loss in pipe flows is commonly referred to as a head loss. The functional losses are mainly caused in the straight pipe. Friction loss induced in fittings such as bends, couplings, and valves, or transition in hose or pipe accounts for minor losses. The frictional losses are recurred to a major loss. It is denoted by H small f, while losses through the pipeline fittings, etc., are called minor losses. It is denoted by H small h suffix m. Together they make up the total head loss is denoted by small h for pipe flows. In practice, loss in the pipe flow comes into the picture in case of calculations of rate of flow the pipes connecting to reservoir as at different levels, or to calculate the addition head is required. The addition head required to double the rate of flow along the existing pipeline. The pipes with a smooth surface does not account for large friction loss, whereas the pipe with less smooth walls such as concrete, cast iron, and steel fluid requires a large energy to overcome the friction induced in a pipe due to the viscosity of liquid. Rougher the inner wall of the pipe, more will be the pressure loss due to the friction. This is the internal surface smooth, and this is the rough pipes. Here the smooth pipeline, the diameter here denoted by d, and rough pipe delta by d is equal to 0, but rough pipe 0 less than delta by d and less than 1 by 2.4. And a rough pipe, this is a rough pipe, the side view, this is the front view. You can see a rough pipe delta by d is equal to 1 by 2.4. It is a porous media. Normally the friction loss in pipe, the friction loss in uniform straight section of the pipe is known as major loss, is caused by the effect of viscosity. The movement of fluid molecules against each other, against the possibly a rough wall of the pipe. So here is greatly affected by whether the flow is laminar or turbulent flow. Okay, laminar means this is a laminar flow, turbulent means is waving one. The laminar flow it occurs when the fluid flows is parallel layers without adjacent mixing between the layers. In this type of flow, there are neither eddies nor cross currents with fast flow over the center part of the pipe, and no movement near the pipe surface. The roughness of the pipe surface influences neither the fluid flow or nor the friction loss. For laminar flow, Reynolds number RE always less than 2100. Okay, next one is the turbulent flow. So the turbulent flow is moving like this. Okay, it occurs when the liquid is moving fast with the mixing between the layers. The speed of the fluid at point continuously undergoes changes in both magnitude and direction for turbulent flow. So in this Reynolds numbers normally is represented 2100 less than RE and less than 4000. Okay, 4000 less than RE less than 2100. And the transitional flow is nothing but it is a mixture of laminar and turbulent flow. Okay, there's always is Reynolds number is RE greater than 4000. Continue பண்ணுவோம். I'm going to conduct the experiment. This is the experimental setup for pipe friction. See the pipe friction apparatus specification here mentioned. The length of the pipe is 3 meter and diameter of the pipe is 20 mm and 25 mm. The motor is 0.5 HP. This is the motor. Okay, and this switch on off switch. Okay, then this is called as manometer, differential manometer here available. In this differential manometer filled with mercury. Then this is called collecting tank. Okay, this is called collecting tank, and two different diameter pipes already connected. So in this pipe is 25 mm diameter, and this is 20 mm diameter. At the time of experimental condition, any one pipeline only open, remaining pipe we should always kept it close. Okay, so now I am going to select first pipe. Diameter is 25 and this in this pipe length is 3 meter. Okay, so 3 meter. Before we start the experiment, first should remove the air block from in this manometer. So now what is the main objective for in this experiment is to determine the friction in pipes. What are the apparatus required? Pipes having different diameter connected to a differential manometer, a collecting tank, stopwatch, scale. Okay, so these are the very important apparatus for in this experiment. And the pipe diameter already told there are two different diameter pipe, 25, another one is 20. So first of all, a pipe of the required diameter is selected from the setup. Okay, then go to next step. Except for the selected diameter pipe, the rest of the pipes are closed. Okay, so 25 only open and 20 is closed condition. Okay, 20 is closed condition. Then this is the manometer reading. In this, the main inlet valve is open to allow water to flow through the selected diameter pipe. You open the pipe valve. Okay, and change knot. Okay, this is called knot. Change a knot of manometer from isolate position to air vent position to air to remove the air inside of the pipe. Okay. Now change knot to reed position. This is called reed position. When the steady flow is reached inside the pipe, turn on the exit valve of the collecting tank to allow the water flowing inside the pipe continuously flow. This is the main outer valve. Okay. So now the experiment setup are over. Now I am going to start the experiment. Okay, switch on. Okay. Now I am going to open 25 mm diameter pipe. So in this 20 mm pipe always kept in closed condition. Okay, by using with the help of in this valve should close in this 20 mm because in this pipe only we can conduct friction, how much friction loss occur. Okay, so before going to start you should always open in this outlet valve. In this valve is connect to collecting tank, water collecting tank. Okay, now I am going to start the machine with help of stopwatch. See, this is the measurement. So this is the null position. So every 5 centimeter water rise in this collecting tank. We note how much time is consumed. That time you should note down. என்ன பார்க்கணும் அப்படி திருப்பக்கூடாது, அப்படி தான் வைக்கணும். Now I'm going to start the experiment. Okay, the 25 mm diameter valve fully open. Okay, fully open. The outer valve also open, but before you're going to start, you should close and then note down how much up to 5 centimeter up to 5 centimeter level increase in this water level height. How much time is uh, you should note down. Okay, so now I'm going to start it. See, the level is 2 centimeter. So 2 means exactly 7. The water level reached means then the time note down up to 7 centimeter. Now I am going to now I am going to close the outer valve. See, the 4 up to 9. Stop. Here the time is 15.60 for 25 mm diameter pipe friction. So note down. So what is the manometer reading? See the manometer reading. Here left limb is 13.5, right limb is 77. Okay, left limb is now. So now I am going to start the second trial. Okay, so up to this level, how much time taken by using the help of stopwatch we can calculate. Okay, the time is 26.30 and the manometer values are 16.5 and 21. Okay, again I have to increase the pressure. Left limb is 18.5. See, 18.5. So left limb is 18.5, right limb is C, exactly 19. Okay, exactly 19. Now I am going to close the outer wall. So now I am going to start the third trial. So up to 7 centimeter level, how much time is taken, noted by stopwatch. So up to 7 level. Check the parameter reading. Already noted. Okay. See the collecting tank. Very low pressure level water filled into this collecting tank. Okay. See the water level. Because the friction is very high, the flow also very less. The pressure also increase. Okay. See the level. The level will reach up to 7. Okay, now time is over. The time noted 57.69. So now all the values are observed from the experiment. Next we will do the calculation. Okay. So now the pipe friction for 25 mm diameter pipe experiment is over. Now I can close 25 mm diameter pipe. Now I am going to open 20 mm diameter pipe. The same procedure repeat again. We'll take another 4 readings and then calculate. Okay. Thank you. Thank you. Now I am going to calculate a friction pipe calculation. This is friction pipe tabulation. Diameter of the pipes are 25 and 20. Two different diameter pipe here used. First one is 25 mm. So with respect 25 mm diameter, what are the manometer readings? So all the values are tabulated here, and the times also noted. The time for 5 centimeter rise of water, all the values are noted and tabulated here. After that, we calculate actual discharge and velocity and friction factor. Area of collecting tank is 2500 centimeter square. Now I am consider first reading from the tabulation, the trial number 1. The dia of the pipe is equal to 20 mm and length of the pipe is equal to 3 meter. Left limb reading values are 23 centimeter and right limb readings RL is equal to 14.5 centimeter. Then we can calculate the head loss. The head loss formula is 12.6 into 23 minus 14.5. The 23 and 14.5 values are with respect H1 and H2 limb from manometer. Okay, the final answer is 107.1 centimeter. The initial reading is 55 centimeter and final reading is 65 centimeter. The water level rise how much? 5 centimeter. It is denoted by small h. Length of the pipe 3 meter and diameter of the pipe is 25 mm. These two are constant, and area of collecting tank already measured. It is denoted by capital A. The value is 2500 centimeter square, and time taken T is equal 14.43. This is the first reading time. And next one is acceleration due to gravity is equal to 981 centimeter by second square. Afterwards, we can calculate actual discharge and velocity and analytical friction factor. The first one is actual discharge. The formula is A into H divided by T. Already all the values are available. You can directly substitute in this formula. Area 2500 and H 5 centimeter and time for first reading 14.43. The final value is 866.25 centimeter cube per second. Then we can calculate velocity V. The unit is centimeter per second. The formula is Q actual divided by pi into d square by 4, and Q actual value already found 866.25 divided by pi into d value is 25. So 25 square by 4. Suppose you are using 20 mm diameter pipe, means you should substitute 20 here. The final answer is 176.47 centimeter per second. After that, analytical friction factor F is equal to 2gd by V square into H by. Next one is analytical friction factor. It is denoted by small f. The formula is 2g d divided by v square into h by L. H means head loss and divided by length of pipe, and 2 into g, the gravity and diameter is 25, and v square, the velocity already found. So all the values are substituted in this formula, will get 0.0562 analytical friction factor for 25 diameter pipe. Okay, afterwards 25 mm diameter pipe closed, then 20 mm diameter pipe open, then conduct experiment, again the same procedure, and observe all the values and tabulated. Then find out again Q actual and velocity and analytical friction factor. Then fill in this tabulation. The first value are calculated, actual discharge and velocity and friction factor for 25 mm diameter pipe. After that 20 mm diameter pipe. So the same procedure repeat again for 20 mm diameter pipe. The same procedure repeat again to calculate second and third readings. Then we'll find out actual discharge and velocity and friction. Once 25 diameter calculations are over, then 25 mm diameter pipe closed and 20 mm pipe open. Again we'll take all the reading and calculate actual discharge and velocity and friction factor. Okay, so this is the procedure for friction pipe. Thank you.